So the sections we have for today are kind of long, but we're going to try to skip the stuff that we don't actually need because I can do what I want. Now 4.5 is about roots of polynomials. It's called real zeros of a polynomial function, and 4.6 is about the complex roots or complex zeros of a polynomial function. Really, these should be done together because, well, they're going to require the same type of work, except the complex roots from polynomials are going to require just one extra little step, and that extra little step is going to be the quadratic formula. Now, polynomials in general can be hard to find roots for. So if we take an example, 2x cubed plus x squared minus 13x plus 6, and we set this equal to 0. When we're finding a root or 0, this is what we're trying to solve. We want to solve for x. Now, really what it's going to boil down to for these sections is we're going to factor them, because when we factor things, we find the roots. You might remember this from our first polynomial section. If f of c equals 0, then x equal to c is a root, or x minus c is a factor. Unfortunately for us, factoring can also be very difficult. In my cubic that I have here, before today, the only thing I could try to use is factor by grouping, and factor by grouping will not work for this polynomial. So then you might ask, well, maybe there's just a formula I can use to get the answers out of it. Well, we have a quadratic formula. If I have ax squared plus bx plus c equal to 0, then my answers are x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And in fact, if you go to, let's see, Wolfram Alpha, and you type in ax squared, I don't want to confuse you, we don't really need that, ax squared plus bx plus c equal to 0, and the little box they give you, it will give you the solutions as the quadratic formula. But just to match up with the problem we have here on the example, go ahead and try to type in ax cubed plus bx squared plus cx plus d equals 0 and see what you get out of it. You're going to get something which is like the quadratic formula, but is way, way bigger. And just for fun, you can also do this up to the 4th degree. And you will also get a formula for the solutions for that, which is going to be even bigger than the ones for the cubic or degree 3 polynomial. And in fact, no formula can exist. In fact, it's provable. There cannot exist a formula to solve, no formula can exist to solve 5th degree polynomials. So I'll say it degree 5 polynomials. So what are we to do if we have some polynomial and we want to try to factor it or find the solutions? We're going to find out when it's equal to 0. Well, we have some information we can get out of the way here. So here's an extra little fact. We have the division algorithm. You might have seen this in the past. This would be A equals BQ plus R. Let's get a better Q in there. Oh, come on, pen. Where R is between 0 and B. Strictly less than B, but it's allowed to be equal to 0. And what this represents actually is if I'm doing division, A divided by B, I'm going to get a quotient plus a remainder fraction. We get the same thing for polynomials. So if I'm working with polynomial functions, I'd be looking at f of x equals, g of x times q of x plus r of x, where r is the remainder polynomial. The degree of r is less than the degree of g of x. And we've kind of already done this without doing it when I talked about the polynomial long division. This is the division of polynomial functions. F of x divided by g of x gives me, a quotient polynomial plus a remainder polynomial. So this would be my asymptote here. And I have a remainder, which I don't really want to deal with when I'm trying to graph these things. But most importantly, out of this, if we suppose if g of x is equal to x minus c, for example, a simple factor, then what this serves as is a test. It's not a test we're actually going to use, but it's going to give us another test that we can use. So let's look at this in terms of dividing by x minus c. I'll be looking at f of x equals x minus c times q of x plus r of x. But if we look, if we try to plug in c to all of this, in place of x, we see that f of c is equal to r of c. So what does that tell us? Well, this gives us a remainder theorem, which goes back to our facts with roots and factors, how they mean the same thing. If f of x, a polynomial function, is divided by a factor x minus c, the remainder is f of c. This goes back up to here because my remainder has to be strictly less than the degree of what I'm dividing by. So if I'm dividing by a degree 1 polynomial, this guy has to be constant. It has to be just a number. Now, what this tells us is kind of the same thing as what we had before. So equivalent to this, let's see, x minus c is a factor if and only if f of c is equal to 0. We've already gone over these things, but it's a nice reminder. This statement I have down here, the book is actually calling the factor theorem, but we actually don't care about labeling these theorems. All we really need to know is that if you divide by a factor, you're going to get a remainder of 0. Which is useful for us because we're going to skip the extra information out of this. So if anybody goes through the book or the suggested problems, we're skipping Descartes' rule of signs. Let me get the spelling right on this. There's an S in there. And the reason I'm skipping it is because it's a little fact to help us say how many roots there are, or how many factors there are, but we don't really care so much as we care about actually getting the factors. The Descartes' rule of signs won't help me get the factors, and so I don't want to talk about it because it doesn't help me as much as I want it to. So what we're going to set up with is the rational root test. And this is our heavy hammer. This is pretty much the only thing we can do when we don't have an easy factoring method available to us. So let's set it up. We have a polynomial function. It'll be a degree n, so I have a sub n, x to the n. Really just a generic polynomial, a n minus 1, x to the n minus 1, plus blah, 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 all the way down until we get to a1x plus a sub 0. And the rule for this is every coefficient must be an integer. You can get away with it if you have rational numbers as coefficients, because what we're doing is we are setting it equal to 0, and so we can freely multiply by a common denominator and force every coefficient to be integers. But this is the setup of the theorem, and so we can't really stray from that. So if every coefficient is an integer, then the theorem says that if there are any rational roots, they must be of the form P over Q. Let's not put a period there. Where P divides the P divides the last number, a sub 0, and Q divides a sub n. Now what this is saying is that all of my rational roots, they're going to be a fraction. The numerator has to be a factor of the constant coefficient, and the denominator has to be a factor of the leading coefficient. And every rational root, including the whole number roots, are going to look like that. But if I have any irrational roots, let's say this, it's no help for irrational roots. Like square root of 3, for example. So let's take our polynomial and we'll do the rational root test on it. Let's see, we've got 2x cubed, the one we started with, plus x squared minus 13x plus 6. We're setting equal to 0 because we want to find out what the roots are. And let's see what this says. We are looking for possible rational roots. So on the top, we use the constant coefficient. The factors of the top, we have plus or minus 1, 2, 3, or 6. And for the bottom, we use numbers from the leading coefficient. We can have plus or minus 1 or 2. So this will be fun. All of my possible rational roots are going to look like fractions. So I can have plus or minus 1, 2, 3, 6, or 1/2, or 3/2, or there's no or, they're already covered. So these are all of my possible roots. So what we have to do now is we have to test them. If f of c equals 0, c is a root, and x minus c is a factor. Now what I would normally have to do is go through all of my numbers, positive version and negative version, and I plug them into my function. And then I find out, do I get 0 or some other number? And what that's going to take the place of, actually, we go all the way up here. If I plug in my potential factor, that's going to give me the remainder of division by that factor. So if I plug in 1, let's go back down. We're going to get 2 times 1 cubed plus 1 squared minus 13 times 1 plus 6, which works out to, let's see, 1 times anything is itself. So we got 3 minus 13 plus 6, which works out to 9 minus 13 is minus 4. So what this says is if we tried let's see, what did we try? If we tried to do x plus 4 divided into my polynomial, 2x cubed plus x squared minus 13x plus 6, and I did all the work, I would get a remainder of minus 4 at the very end of all my work. But I don't want to do all that work. It's easier to just plug in the number and see if I get 0. So 1 didn't work. Let's try 2, because I don't really want to plug in negative numbers right now. We can fit that here. Whoops, that's not working. There we go. Try f of 2. So what do we get? 2 times 2 cubed plus 2 cubed, nope, squared minus 13 times 2 plus 6. Let's see, this is 2 times 2, and that's squared, so that'll be 16, because 4 times 4, plus 4 minus 26 plus 6. And if I add up all the positive numbers, I'll get 16 plus 10, which is 26, minus 26, which is equal to 0, which is good. So what this is telling me is, whoa, x equal to 2 is a root, or x minus 2 is a factor. So what I want to do is I want to take my polynomial and divide it by x minus 2, and that way I'll have something smaller to work with. So we save this information because it's going to be part of our final answer, but we're going to do the long division to decrease the size of my problem, in a sense. 2x cubed plus x squared minus 13x plus 6. And I want to do all of this division. So let's see, to get 2x cubed from x is 2x squared. We'll be subtracting minus 2x cubed minus 4x squared. So we get 0, x squared minus a negative 4x is 5x squared. Take that down. If I want 5x squared out of x, I need to multiply by 5x. Multiply this down, I'll get 5x squared minus 10x in there. So we get 0 here. Minus 13 minus minus 10. So minus 13 plus 10 is minus 3x. I can pull this down, plus 6. Now if I want a minus 3x out of x, I need to multiply by minus 3, so that's there. And what I end up subtracting is minus 3x plus 6. And I have a remainder of 0, just like I should. So we wanted to factor my original polynomial. I found one factor, I did long division, and now I have something smaller to work with. Because what this basically says is that 2x cubed plus x squared minus 13x plus 6 is equal to, and this is from that division algorithm we saw before, x minus 2 times 2x squared plus 5x minus 3. So we have a partially factored answer. Now what we need to do is we need to factor this quadratic that we've been stuck with. I think we can do this easily. Let's try it. Let's see, 2x times x. If I do a 3 and a 1, then I will want minus 1 and plus 3. So let's check this. 2x times x is 2x squared, plus 6x minus x gives me 5x, ending with a minus 3. So I've successfully completely factored my polynomial now. Now what we could have done is at this stage I could have repeated the rational root test, which we would need to do if I start off with a very large degree polynomial. So if I started with a degree 5 polynomial, I could do rational root test. That would decrease me down to a degree 4 polynomial. And then I would have to do rational root test again, unless I had a really nice looking polynomial. And then I would decrease that down to degree 3 polynomial. And then I would have to do rational root test again, decrease that to a degree 2 polynomial, a quadratic, and then I could either do the rational root test again, or I could try to factor it manually, or I could just use a quadratic formula. The problem with the quadratic formula is it doesn't tell you about this coefficient on the x. So after the first test, we may repeat the test as needed. But if I'm looking for my roots, we have that the roots of f of x, oops, that's not going to fit, f of x equal to 2x cubed plus x squared minus 13x plus 6. This will give me x equal to, what do we get? 2, 1/2, and -3. So you can give it a shot here. You can start with plugging in 1/2 to the original function. You're going to get 0, and then you can try to do the long division with that. You'll get a different looking polynomial, but at the end result, after you do all of your factoring, you should get the same set of answers no matter what. Now, our book has some additional things about trying to guess where roots are and stuff, but that's material which is covered again in calculus and is not going to be innately helpful for us in this class right now. So let's move on to the complex numbers. And I'll have another video up to deal with how complex numbers work. Fortunately, we don't really need to know how they work in order to get them as answers. But if you remember when I talked about the fundamental theorem of algebra, algebra, a degree n polynomial has at most n real roots. And what I'm missing here is, here I should say, with real coefficients. But as an addendum to this, since we're talking about complex numbers, is a degree n polynomial has exactly n roots. But they're not real roots, they're complex roots. And it doesn't matter what kind of coefficients we have here. So I can say real or complex coefficients. I think the books like to avoid using polynomials with complex coefficients because they don't look quite so nice. But the fact is, you can have complex coefficients if you really wanted to. Oh, geez. Now, something about complex numbers. Well, something about numbers. What kind of numbers do we have? We have natural numbers, which is like 1, 2, 3, etc. We have integers. Which is positive and negative. 1, well, we have to include 0. 0, plus or minus 1, plus or minus 2, etc. Then we have rationals. That's with a Q, and those are all your fractions. So I'm just going to say fractions of integers. And then we have real numbers. And then beyond that, we have complex or fake numbers. So this is a plus bi. I equals the square root of -1. So if you remember, we can't take the square root of negatives because they're not real numbers. Or there is no real number answer that is the square root of a negative number. So they're fake numbers. They're imaginary. And the reason I've listed these out here is they are all contained in the higher number field. So complex numbers, they contain real numbers. That's actually the first part of a complex number, if I let the second part be 0. So they contain all of the reals. The reals contain all of the rationals contain all of the integers contain all of the natural numbers. So a real number is a complex number with a 0 coefficient on the imaginary part. So what we're going to see is that I'm going to continue factoring some of these polynomials beyond what should normally be possible. So for this one, we're just going to take a relatively simple example. Start with p of x equal to x cubed minus 3x squared plus x minus 3. Now, I don't have to do the rational root test on this one, but I can. So I'm going to say possible rational roots. We're looking at plus or minus 1 and 3. So we have an easy setup for this one. But I can actually factor this one by grouping. So I'm going to do that. Is equal to x squared times x minus 3 plus x minus 3. I can factor out x minus 3. Whoa. And I'll be left with on the inside x squared plus a 1 left over. Now before now, this would be considered completely factored. This is completely factored as far as the study of real numbers. There's only one real root, which is x equal to 3. But I can't find a real number where if I square it, I get negative 1. So what I have, if you were to graph this, you would see it crosses the x-axis exactly once, and it's going to take a cubic shape, so it goes up and then down and then up. But the part where it goes down doesn't cross the x-axis again. But we can continue factoring since we're dealing with complex numbers. So if x squared plus 1 is equal to 0, that means x squared is equal to minus 1, which means that my x is equal to positive or negative square root of negative 1, which is plus or minus I. So these are my complex roots. If I wanted to write it in terms of factors, I'd be looking at x minus 3 times x minus I and x plus I. But that's not really a that's not a super good looking factored form. In general though, we may have more complicated issues, so we'll do another example. Here I've got f of x equal to x cubed minus 2x plus 4. Now we don't have any shortcuts we can use with this one. We're going to have to use the rational root test on this because it's a cubic and I can't do factor by grouping. So let's list the possible rational roots. I take the factors of the last number divided by factors of the first number, and I have plus or minus versions. So I can have plus or minus 1, 2, or 4. We're going to save some time and just say, hey, it's going to be minus 2. F of minus 2 is equal to, let's see, what do we get? We're going to get minus 8 plus 4 plus 4, which is 0 in the end. So if I do the long division, I'm going to skip the long division for this one. I'm going to get f of x is equal to, I said minus 2, so this is x plus 2, and we're stuck with x squared minus 2x plus 2 as a result. But we want to keep going. We have all of the real roots now, but we also want the complex roots. We're assuming that we're going to get complex roots out of this. So let's find out. I want I have x equal to 2 plus or minus the square root of 4 minus 4 times 1 times 2 minus 8 all over 2, which works out to, let's see, 2 plus or minus the square root of minus 4 all over 2. And I can take the 4 out. So this is 2 plus or minus 2, because the 4 is 2 times 2. It comes outside of a square root as 2, but I still have a minus 1 in there, all over 2. I can factor and cancel the 2's. I end up with 1 plus or minus square root of negative 1, or I could say 1 plus or minus I. So I have my real root. It's just one of them. That's negative 2. And I have my complex root. Actually, I get complex roots. 1 plus I and 1 minus I. Now you notice the one I had before, it had a plus or minus 2. It had a plus I and a minus I. And there's a nice little fact that comes from the complex roots, is that they always come in pairs. Now what a conjugate pair means is you've got a plus version and a minus version. So if a plus bi is a root of f of x, meaning f of a plus bi is equal to 0, then so is a minus bi. So a minus bi is the conjugate of a plus bi, and vice versa. Now, part of the result of this is, I've said this before, that an equivalent statement for the fundamental theorem of algebra is that every polynomial with real coefficients can be factored into linear and irreducible quadratic factors. It's because we're just one step away from having the complex version that says a polynomial has as many roots as its degree. As far as looking at f of a plus bi, you can use a calculator, an intelligent calculator, or one of those online services to set you up with that. But once we do the video on complex numbers that I'm going to add, it should be a little clearer on how that works out when you start multiplying complex numbers together. At any rate, this is the last bit of information we need for this chapter, and therefore it's the last bit of information we need before our next test. So you guys have that to look forward to next week.